Hi guys! So in this chapter, we're going to be working with bivariate data. Bivariate data are data in which two variables are measured on an individual. So for example, we might want to know whether the amount of soda consumed per week is related to one's bone density, right? So the individuals will be the people in the study, and the two variables will be the amount of soda and bone density, right? Or we might want to know whether the amount of study hours per week is related to a student's test score, right? So the individuals will be the students in the study, and the two variables will be study hours and test score, right? So notice that these variables, amount of soda, bone density, study hours, and test score, these are quantitative, right? So in this chapter, we're going to learn methods for describing, so that's actually the title of this chapter, describing the relation between two quantitative variables. That's what we're learning in this chapter, right? So quantitative variables, right? Okay, so let's go ahead and talk about the key term and notation. Okay, so correlation. Okay, so correlation is a measure of association between two variables. So that's what we call correlation. Okay, so the two variables that we will be working with are called the explanatory variable and response variable. And the traditional letters to use for explanatory and response variables are X and Y. So X is often referred to as explanatory variable or predictor variable. And Y is often referred to as response variable, okay? And also, samples of bivariate studies are collected as ordered pairs, X comma Y, all right? So what is explanatory variable, right? Well, it is the variable whose value can explain or may influence changes in the response variable. And the response variable is the variable whose value can be explained by the value of the explanatory variable. So for example, right, your study hours might be able to explain how well you do on the test. So we might use study hours to predict a student's test score. So in this case, we call test score the response variable. And study hours, the explanatory variable. Okay, how about the amount of soda and bone density, right? Well, we might use the amount of soda to explain or predict one's bone density. So there might be an association between these two variables. So in this case, we call bone density the response variable. Okay, and the amount of soda, the explanatory variable. Okay, now the first step in identifying the type of association or relation that might exist between two quantitative variables is to draw a picture of the data. And the picture is called a scatter diagram. So a scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the dataset is represented by a point in the scatter diagram. And the explanatory variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. Okay, so let's take a look at an example. A golf pro wants to investigate the relation between the club head speed of a golf club measured in miles per hour and the distance in yards that the ball will travel. He realizes other variables besides club head speed determine the distance a ball will travel, such as club type, ball type, golfer, and weather conditions. So to eliminate the variability due to these variables, the pro uses a single model of a club and ball, one golfer, and a clear 70-degree day with no wind. The pro records the club head speed, measures the distance the ball travels, and collects the data in Table 1. Now, it looks like the pro wants to use club head speed to predict the distance the ball travels. So that means club head speed is the explanatory variable. Okay, so this is, you know what, let's write like this. So this will be the explanatory variable, and the distance a ball travels, that will be the response variable. Okay, so this will be X and this will be Y. So let's take a look at this table here. So club head speed data is on the left, so that will be X, and then distance will be Y, right? Okay, so the first ordered pair is 100, 257, right? And then the second one is 102, 264. Okay, and so on, right? The third one is 103 miles per hour, and that corresponds to 274 yards, and so on. Okay, so we have, let's see here. We have 1, 2, 3, 4, 5, 6, 7, 8 ordered pairs. So if we plot these ordered pairs in a rectangular coordinate system, we get a scatter diagram on the next page. Okay, so take a look at this scatter diagram, right? So the ordered pair 100, 257 is here. And 102, 264 is here, this point right here. Okay, and so on. So there are a total of 8 points because we have 8 ordered pairs, right, of data. And the explanatory variable is club head speed, and it's on the horizontal axis, right? And the response variable is distance, and it's on the y-axis. Okay? So from the graph, it looks like as the club head speed increases, the distance the ball travels increases as well. I mean, we do see that points are going up and down, but in general, the graph is going up from left to right. Okay. Oh, by the way, do not connect points when you're drawing a scatter diagram. Okay. Just plot points and that's it. Do not connect them. Okay. So let's learn how to describe an association between two variables. So to describe association, we will start verbally and then we'll describe association mathematically. Okay. So we can describe association verbally in 3 ways. The first of which is what we call the direction of association. So we're going to say that the direction of association is either positive, negative, or neutral. Okay, so going up or going down, or it's not either going up or going down. Okay, it goes flat, right? Then we have the strength of the association. Okay, and the strength of the association can be either strong, moderate, or weak. Okay, and then we have the shape or a form of the association. Okay, so variables can be associated in a linear fashion, or they could be associated in a fashion that is not linear. So linear or nonlinear. So we're not going to get into these nonlinear associations, okay? But you could say, for example, that an association might follow very popular models such as exponential, polynomial, logistic, logarithmic models. But in this class, we will focus on linear associations only, okay? Now, when we talk about the direction of association, okay, we're referring to the notion that if the value of one variable increases, the value of the other variable also increases. Or if the value of one variable increases, the value of the other variable decreases. So if we say that the direction of association is positive, right? This essentially means that as the value of x increases, so as x increases, the value of y generally increases with it in response. Okay, now it's not going to be perfect. One of the major differences between statistics and algebra is that in algebra, usually things line up nicely, right? But in statistics, when we collect data, things are not going to always respond in the way that you like them to. But in general, as the value of x increases, the value of y will increase in response. Okay, and here's an example of how it looks like. Like that. Okay, it's going up, right? Now, if we have negative direction of association, then as the value of x increases, the value of y generally decreases with it in response, okay? So as x increases, y generally decreases in response. Okay, so this is what we mean by a negative association, and here is an example of how it looks like. Like that. Okay, so going down this way. And you can also have what's called a neutral direction as well. Okay, so what does it mean for an association to be neutral? Well, essentially, there is no clear direction at all. No clear direction, and this is how it looks like. Kind of like that. So points are kind of all over the place, and there does not seem to be a general pattern in the direction of association at all, right? And that could be just as interesting depending on the study that you're conducting. So again, neutral, all right? So no clear direction of association. Okay, now let's go back to the scatter diagram of distance versus club head speed really quick. And it appears that club head speed is positively associated with the distance, right? It's going up, right? So the direction is pretty clear. So it's a positive association. Now, when it comes to the strength of the association, right, we're talking about essentially the degree of clarity in the association. Degree of clarity in association. Okay, so we're looking at how clear the direction and the shape of the association are, right? So when we say that the association is strong, right? Let's start with that one, strong. Okay, that essentially means that the direction and the shape or form of the association are very clear. Okay, so we have a very clear, we're being a little bit loose here, association, which is basically is the direction and the shape are clear. Versus weak association or moderate association means that the direction and the shape of the association are not as clear, right? So weak or moderate. Okay, that means association is not as clear. I will give you a couple of examples, but let me talk about the shape of the association first, okay? All right, so the shape or form of the association essentially does what it sounds like, right? It describes what kind of shape the data essentially will make when you look at the data displayed in the scatter diagram, right? So it's the shape of a general pattern of plotted data. Okay, now the most popular one that we're going to look at is the linear versus nonlinear. So essentially, it does what it sounds like. The dots sort of line up in a linear shape or not. The dots that do not line up in a linear shape might have a curved shape in a plane. And as I mentioned earlier, and we're not going to, I mean, we're going to focus only on linear associations, right? So we're not going to cover models such as exponential, polynomial, logistic, logarithmic models, such, stuff like that. So, okay. Now, going back to the scatter diagram of distance versus club head speed, right? I would say that the association is pretty strong because the direction and the shape of the association are pretty clear, right? So it's a strong, positive, and I would also say that the association is probably linear, okay? So a strong, positive, linear association between club head speed and distance, okay? So here's another example. Let's say we want to describe the associations using only the given scatter diagrams, right? So we have 3 diagrams here. So we can use the 3 features, the direction, the strength, and the shape, right? Okay, so first one, A. What do you guys think? I would definitely say that the direction is positive, right? Since as x increases, y increases with it, right? I would also say that the association is pretty strong because the shape and the direction of the association is clear. Okay, so it's pretty strong. Okay, and I will also say that the association is probably linear. Okay. Now, for B, I would argue that the direction is not as clear as the first one, but in general, x increases, right? If x increases, then y decreases with it, right? So it's going down this way. So I would suggest that the association is probably negative. Okay. I would also suggest that the association is probably not as strong as the first one because the shape is not as clear. Okay, so weaker, right? And I would still argue that the association is linear though, but the shape is not as clear. Okay, so I will write like linear, maybe. Okay, now for C, there is just no pattern at all, right? The dots are pretty much all over the place, right? So in this case, we would simply say that there is a neutral association. Okay, there does not seem to be clear direction or shape at all. Now, just looking at pictures and verbally describing an association is not enough for us to determine if there really is an association, because pictures can be subjective, right? You can also change the way that your axes are scaled, and you can actually change the way the picture looks. So there's a more mathematical way to do this, and it's called a linear correlation coefficient. Okay, so very important definition. The linear correlation coefficient quantifies the direction and strength of a potential linear association. The Greek letter rho represents the population linear correlation coefficient, and R represents the sample linear correlation coefficient. Okay, now we're always going to use a calculator to compute the correlation coefficient because the formula is very cumbersome, right? But just for kicks, okay, we're gonna go ahead and take a look at this formula so we realize that it is not something that you want to deal with, okay? So the formula for R, so we're gonna focus on the sample linear correlation coefficient, R. Okay, so this is the formula right here, right? So R equals, so you have to take the sum of the ith observation, xi, right? Xi is the ith observation of, explanatory variable, okay, xi, right? And then minus the sample mean of the explanatory variable, so x bar. Okay, so that's the sample mean of explanatory variable. Okay, and then divide that by divide the difference by the sample standard deviation of the explanatory variable. So that'll be Sx right here. So that'll be sample standard deviation of explanatory variable. Okay, so you calculate this part, right? And times the ith observation of the response variable, which is yi, right? So yi is the ith observation of response variable minus y bar, which is the sample mean of the response variable, right? And divided by sy, which is the sample standard deviation of the response variable. So you have to find this product, okay, for all observations, and then add all the products, okay, and then divide that sum by n minus 1. N is the number of individuals in the sample. So N is the number of individuals in a sample. Okay, so again, your calculator is going to do all these for you, so you don't need to know this. But if you look at this formula, right, there is an easier way to write it. It's actually the sum of the products of the z-scores for A and Y divided by n minus 1. Z sub x times z sub y. Remember the z-score formula? That's data minus mean divided by standard deviation, right? That's this. Okay, so this is z-score for explanatory variable, and this is z-score for response variable. Okay, and then divided by n minus 1. Okay, but yeah, but use TI shortcuts for this. And I'll show you how to compute linear correlation coefficient in the next video. All right.